He's from the beginning, he's been working with optics, and in fact, his basic degree, as I was seeing from IIT Bombay, was on engineering physics. So he's always been part of the quantum world, I would say, maybe since his engineering days. And then later he went to Carnegie Mellon University to do his PhD. And then many quantum companies he has been associated with, especially QNew Labs. You would have heard about QNew Labs. Some of the resource persons have also worked there. So QNew Labs was one of the what do you say startup which came out of IIT Madras, and I'm so happy you can visit the LinkedIn profile and see more details about sir. And one of the most important thing that is important for us and for our country is that sir is the project director for the National Quantum Missions Hub on quantum communications. So it's a joy that today we have two eminent personalities. One is Professor Anil Prabhakar, and after his session, we will be joined by Dr. L. Venkat Subramaniam, who is the IBM India quantum leader. So both these sessions, they will be giving you an overview and also giving us challenges for our country. So as you will be addressing the students in your respective colleges, you will need these vision to be imparted back to them. So please listen, and please remind your friends who are yet to join. About 240 have already joined, but I am sure that many more are will be joining shortly. Please remind them. We have just preponed this time, as you all know. So kindly ensure that your friends are reminded. Just message them and remind them once. And let's hope that we'll have a very useful time. Of course, the recordings are definitely available for you to watch later, but we'll make the most of the time, that this precious time that Professor Anil Prabhakar is sharing with us. Without much delay, I would request Professor Anil to take this lecture forward. Thank you. Thank you very much, sir, for sparing your valuable time.
Well, thank you very much for inviting me. I'm not sure, but please let me know if my audio is giving a problem, and then I will try to fix
Sir, as of now, there is no problems. Yeah, it's
okay.
fine.
There was a problem at my end because I think my other device is also talking to me. But
Right.
that's okay. Let me share my screen, and then you can take it from there. Right. Okay.
Yes, sir.
All right. So what we're talking about here is what I call building quantum secure networks. You have already had some introduction to um, quantum communications, and hopefully you have some of the basics in place. But I'm happy to take questions. So please do alert me if I don't leave time for questions. As was introduced, I am now the project director for the Quantum Hub, which is called Samnya. You can go to the link, it's samnya.in. I also am the principal investigator for the Center for Quantum Information Communication Computing at IIT Madras. A lot of the work that I'm going to describe today has been done by a collaboration that includes SETS, CDAC, and will now also include IISc, IIT Hyderabad, and IIT Indore. The original funding came from the Ministry of Electronics and Information Technology, and now it has been absorbed under National Quantum Mission. We'll go very quickly over the goals of the mission, and then I will start telling you some of the details of what you may need to know in order to build something, and then we'll wrap it up. Right? You will hear a lot about quantum computing applications, and I like starting my talk on quantum communications with something like this, because what we are seeing is a reason to do quantum cryptography that is driven by the possible advent of a quantum computer. But that timeline is fairly far out. So the question becomes, do we need to worry about it today? And I will try to convince you that it is necessary. So if you look at the timelines, we are seeing that maybe IBM and Venkat will join us after this lecture. About 2026, they will have more than 10,000 qubits. Google maybe 2029. So this is still in the future. And the question is, why bother about quantum communications today if this is still in the future? Before we go there, please understand that there are many competing technologies for quantum computers. And you will see that there are superconducting photonic cold atoms and so on. And it's a increasing race between these technologies to understand what do we use for. And it might turn out that something like a cold atom or an NV center can break our passwords before a superconducting qubit can. So one has to be aware of this landscape. So why are we looking for a quantum computer? It's very obvious that even a supercomputer today has the equivalent of only about 40 qubits. And if you want to fly, you design an aeroplane, not a faster car. So people are very aggressively trying to build these quantum computers. Um, they may not get there because 40 noise-free qubits will still require them to have maybe 10,000 noisy qubits or more, right? And to actually be able to crack my passwords, I don't know, you probably need a million qubits. So there's still work to be done. And the stack itself, when people think of quantum computing, they're only talking of these physical layers. They're not really talking of all of these layers above it. But look at the algorithms that are there. The one algorithm that everyone talks about is Shor's algorithm. And that is used for cracking passwords. So the question is, if somebody is using Shor's algorithm and can come up with some other architecture, can they crack passwords sooner than later? Or can they, for example, store our data today and use Shor's algorithm later where the quantum processor becomes available to you, right? So that is the other danger. So when do we use a quantum computer? There are only two known algorithms. Well, there's only one known algorithm that gives us an exponential speed up, and that is Shor's factoring algorithm. Um, Grover search reduces the speed up, but you may not see the advantage in the near term simply because we don't have enough noise-free or logical qubits on a quantum computer. So if one starts looking primarily on at Shor's algorithm, that is where the danger is, that it is used for, in simple terms, cracking passwords. Well, I also argue that I don't need a whole country to be learning how to crack passwords, so I don't know why everyone is doing quantum computing. But there is value in doing quantum communications, and I'll explain why. See, look at this security assessment that I downloaded recently from a website of a company. And what it says is that on different hardwares, you can take this much time to crack passwords, right? So if you have only 8-character passwords of numbers only, then in 34 minutes on an A100, your password is cracked. If you use a chat GPT type A100, then it is cracked instantly. If you use a combination of numbers, upper and lowercase, letters and symbols, ChatGPT type cluster will take 3 months to crack your password. And remember, this is not a static target. ChatGPT 5 is already out, right? And the hardware is not stationary. What was last year RTX 4090, which was maybe gamers' hardware, today everyone has access to A100s. So we are looking at an AI-based threat long before the quantum computer comes. What will happen on a quantum computer is different, right? So we have this particular issue. Then, of course, we have alternative methods. So, for example, in June, one of the Chinese groups said that they broke a 22-bit RSA key using a quantum annealer, which is a different type of quantum hardware. So we must be aware that there are multiple ways of solving this problem, which is break RSA encryption. And we cannot be stationary in our outlook. Similarly, in June, there was another quantum computer that the Chinese announced, where they were competing with 1,000 qubits, right? So, what does quantum communication try to do? We are trying to leverage the principles of quantum mechanics to distribute keys between entities and aim for information theoretic security, right? I also like to point out that people will confuse fiber-based quantum key distribution with what is free space that relies on line of sight. Line of sight, most people will say, is satellite. Not necessarily. It could be building to building. It could be ship to shore. There are many such applications, but there is a limit to what you can do on the ground because the Earth's curvature limits you to about 5 kilometers where you hit the horizon. After that, you have to go on towers in order to expand that reach. So if you say, okay, about 5 to 6 kilometers is what you're planning to do, then that is the best you do with line of sight. Unless you set up very tall towers and you uh, account for all the vibrations that occur and the winds and so on. By and large, fiber-based QKD is what we will focus on, and you'll see that there are a number of applications that are expected and about $3.4 billion in revenue. So this is a small picture that explains how it goes. You have a QKD module, you have two channels, a quantum and a classical channel. This QKD modules then establish a symmetric key between two parties, Alice and Bob. And it goes into an encryptor and a decryptor, and there is a ciphertext, which is the encrypted text that passes between the two parties. We must encrypt data in storage and in transit, and that is what this transit is what QKD is trying to do. Right now, I'll show you a small video, and you'll understand how this works. Let me just. So, if you look at this video, I will just talk you through it. There is this gentleman here who has got 3 laptops. He's connected 2 laptops on a fiber. Right? You can see him transmitting his video from one to the other. In the middle, there is a third laptop, which is a sniper. Right? Now, what he's going to do is he's going to connect his sniper onto the same optical cable. This yellow thing in the middle is this optical cable. And he's going to use a small device that he's going to, you can buy it. I bought it off eBay for $99. He's going to take the fiber and he's going to connect it. And what has happened out there is something quite amazing and trivial. He's now got the video coming on the middle computer, right? That middle computer is basically now sniffing on the data that was being sent from the two transmitter and receivers. And you can search for it. You can find the YouTube video. It's, you just search for how to tap into an optical fiber and you'll get it. So that is one thing. We want to ensure that any passwords that go on the fiber are safe. Then, of course, there is encryption. After you have the password, you have to encrypt. The most safe way is a one-time pad, and there is a very simple example out here where you take a plain text, which is a random, which is your data. You have a secret key, which is a random string of ones and zeros. You XOR them. So 0 and 1 XORed is 1, 1 and 1 XORed is 0, 1 and 0 XORed is 1. You get a ciphertext. This ciphertext is then transmitted, and anybody who has the key can recover the original plain text. So the two questions. One is, how many times do we want to exchange the secret key? And there is a standard, the secure shell protocol, that says that every 1 gigabit of data has to have a new key. All right. So if I'm transmitting this at 1 gigabit per second, that means I need a new secret key every second. Right? So how do we distribute these keys? And that is where quantum key distribution comes in. We use both quantum key distribution and post-quantum cryptography. PQC as key encapsulation as well as digital signatures on it. So many people are building quantum networks. There is Italy, UK, USA, Japan, and of course China, which has done 2,000 kilometers of fiber and a satellite demonstration. Notice in here in China, they also have these smaller networks at each of the cities. These are what we call metro area networks, and the long links is what we are aiming for. In India, we have a metro area network called Makan in Chennai. We also have a long link that has been demonstrated between Prayagraj and Vindhyachal. CDOT has a network set up between CDOT and Sanchar Bhavan in Delhi. So building these networks is not very difficult. Scaling them is the challenge. How do you manage it all when you put it together? So the key management in a QKD network comes in 3 layers. You have a quantum layer, you have a key management layer, and you have a communication layer. The quantum layer is where you run QKD. Sometimes the quantum layer is not available or there is a breakdown, in which case you rely on post-quantum cryptography and quantum random number generators in the post-quantum cryptography to generate your keys. And then these keys are transmitted from the key management layer to the communication layer where the encryption happens. It's important to build interoperability into a QKD network. So, different vendors can come with different protocols and different boxes. So maybe in this picture at the bottom, the left side is one vendor and the right side is another vendor. And the people in the middle have to be able to talk to both vendors, right? And that is where the orchestration of a key becomes critical. Coming now to something more fundamental, I will explain to you that there is a certain loss in every fiber. Right? An optical fiber has an attenuation, and you can see that there are 3 windows: first window, second, and third window. The first window has an attenuation of about 2.5 decibels per kilometer. The second window at 1300 nanometers has an attenuation of about 0.5, 0.3, and the lowest is at 1550 nanometers, where it is 0.2 decibels per kilometer. Now, these are textbook numbers. This is not the numbers that we get in the field. But on this textbook number, you can see that 0.2 decibels per kilometer means if I use 100 kilometers, I will get 20 decibels. 20 decibels is translated into 1 in 100 photons will reach. That means every time I send 100 photons, only 1 reaches. So if I go back to this particular slide and say that I have data going at 1 gigabit per second, that is my plain text, and I need my secret key. I cannot really get a secret key at 1 gigabit per second, but I can get it maybe at 1 kilobit per second, right? And that is sufficient because then that's 1000 bits, or I can do 1000-bit AES encryption on my gigabits of data, right? So we need to understand that even the one-time pad is very hard for QKD, and we are actually relying on the security provided by SSH. In this band out here, in this C band, we actually break it up into many channels. And so the C band out here is broken into 40 channels. And QKD will run on some small number of channels out here. So maybe 3 or 4 of them. Actually, it runs on only one of these channels, but we are using the other 2 channels on the side as protection. Right? So we don't allow any classical data there. I'll show you why we don't allow that. Okay, so one of the things, of course, I have to do is stop using Alice and Bob. So I say we'll use Drona, Arjuna, and Ekalavya. Ekalavya is, of course, trying to steal the information that Drona is sending to Arjuna. Right? And the idea is you establish a key with unconditional security from Drona and Arjuna. You use single photons to ascertain the key is based on bits received by Arjuna, and you throw away all the bits stolen by Ekalavya. Right? So there is a raw key that we are transmitting from Drona to Arjuna. We then do what is called sifting. We do error correction, we do privacy amplification, and then get a secure key rate. So where does the security come? The security comes from the fact that if there is anybody tapping into this channel, they introduce an error that we can monitor as a quantum bit error rate. So in another, the same information in another picture, you will see out here the secure key rate is about a kilobits per second. The transmission channel is running at 100 gigabits per second. So that means I'm using the ratio of 10 to the power 10 to the power 8 out here. And we are limited in doing this because our detectors, or what we call SPADs, have a hold off time of 10 microseconds, which can give me a raw key rate of 100 kilobits per second. I take this raw key and I go through these 4 steps and I end up with a secure key rate of kilobits per second. Again, as a reminder, free space is in the first window, 805 nanometers. Optical fibers are in the third window, which is at 1.55 microns. I repeat these things because people continue to mix them up, and I have to keep asking them, what wavelength are you using? So here is a particular way of doing quantum key distribution that is called differential phase shift. And I'll explain very briefly. It's very easy to understand. You take a single photon and send it through the structure of 3 paths, A, B, and C. And then what comes out are three states of the photon. So the photon is a superposition of these 3 time bits separated by the same t that is there in the delay. And what we are doing is putting a phase modulator which takes the raw classical keys and imparts a phase between the first and the second pulse, or the second and the third pulse. Then what we do is we send this down the fiber, and at the receiver, we again have the same short and long arms with the same T. And what that allows us to do then is take the interference between the first and the second, and if it is constructive, it will go to D1, detector 1. If it is destructive interference, it will go to detector 2. If you look at the output out here on a classical channel, it will, on an oscilloscope, you will see this. You'll see that B and C have a higher amplitude than A and B. Why is that? It's very easy to see. If you look at the A and the short, it will happen with 1/6 probability, because there are 3 out here and 2 out here. So that is 3 into 2, there are 6 paths. A and short is 1/6. C and long is 1/6. However, if you look at B and short and A and long, these will come at the same time, and so you'll get 1/6 plus 1/6, which is 1/3. Similarly, if you look at B and long and C and short, they will also come over with 1/6 plus 1/6, which is 1/3. So every time I send a photon and I try to see at which time I make the detection, I will see that in time instance 2 and 3, I have the probability of 30% each of detecting the photon. Now, there is uncertainty in this detection because I do not know if it came through B and S or C and L, or in the third time bin, whether it came through B and L or C and S. So that uncertainty is what we are really using. Now, these are some experimental results. You will see on the right hand side is a quantum bit error rate, which is usually less than 20%. It can go much lower if you optimize the system. I think people have shown even 5%, 4%. What I want to draw your attention to is this red curve, which is what is the sifted key rate as a function of distance. And you'll notice that I pointed out this 100 kilometers. By about 100 kilometers, we are reduced to down to about a kilobit per second, right? So that is sort of the limit, 20 decibels of loss. Same thing is shown in this plot. You will see there are different attacks that people do. One is called an intercept and resend attack, where you have the eavesdropper in the middle, uh, pretending that they can take all the information and send out new information. There is a phase randomized attack. What these attacks all do is that they change the secure key rate. Now this is in per bit. So if I transmit at gigabit per second, then out here I will get about kilobit per second at 100 kilometers. And that 100 kilometers seems to be, if you don't like 100, it's maybe 110, seems to be where there's a huge drop in our key rates. So the secure key rate depends on the type of attacks that we anticipate the eavesdropper will have. If the eavesdropper is more powerful, you will get a lower key rate. If the eavesdropper is less powerful, then you get a higher key, right? But it remains that you have to actually go through these processes. You cannot go through this process and establish, without going through this process, you cannot establish a secure key. I keep emphasizing this because just like in the case of the quantum computer, where only the physical layer at the very bottom had the QPU, everything else was classical. Here also, the classical piece is shown out here in this right. The quantum piece got over as soon as I transmitted photons and I received them. So as soon as I transmitted these photons and I received it, the quantum part of it is over. After that is a lot of hard work on doing sifting, error reconciliation, privacy amplification, and then estimating what the secure key is. So if we look at what NQM is trying to do, it is saying we will do intercity quantum key distribution over 2000 kilometers. We will build a quantum network with quantum memories and synchronized repeaters. We will use multi-core fibers. We will use post-quantum cryptography. So this picture on the left, bottom left, is one of the ITU standards. Again, you will see that you have quantum QKD modules at the bottom. They will be connected to other QKD nodes. And every so often, there is a key that goes to the classical network where there are network devices with cryptographic applications. To the right is a repetition of what I kept emphasizing, that 100 kilometers is sort of where we can get. If you go to longer distances, you can establish a key, but it is at a very low rate, right? Until we can get a quantum repeater. Quantum repeaters are still under research. Putting them into the field is going to take some more work. So what have we done so far? We have got this metro area quantum access network. The metro area quantum access network can take us from IIT Madras to IIT Madras Research Park to SETS and then to the National Informatics Center about 6 kilometers away, right? And we have also shown that it's not just the quantum key, but we also need to do clock distribution, because remember, we are talking of these time bins. Which time bin, time instant does it come in? 1, 2, or 3, and 4? Which means I need to be able to have a clock that is as precise. So if this photon has a width of about 1 nanosecond, that means I should have about 1 nanosecond or 1 gigahertz clock accuracy, right? Or less than that. But the problems are actually not all quantum. The problems are very classic. So I showed you this video of this person tapping into the fiber. In India, you don't have to have even buy $100 device from eBay. You pay the guy who splices these fibers 100 rupees, and he'll give you access to this splice box. And inside the splice box, you can see light is coming off. And we don't even have to tap into this original fiber. I can just keep another fiber on the left of it. Because my detectors on my quantum detectors are so sensitive, it's very easy for me to steal your information and save it. If I can use AI/ML, I will use AI/ML and crack your passwords today. If I have to wait for a quantum computer, I will wait for it. So these practical considerations overwhelm quantum communications, and this is something that we really should understand, that quantum communications is not a magical bullet. If you write your password on a piece of paper, then it is already leaked. Similarly, if you use bad splices along the fiber, then your passwords are anyway being leaked. So we have to be aware that all those splice protector, these plastic things have to be covered to ensure that there's no loss of information. How do we classically determine where the splices are? There is an instrument called an optical time domain reflectometer, and you'll see out here that the OTDR is capturing all these breaks in the fiber. And I just point out that this is, if you look at the y-axis, this is from about 8 dB to about 12, 13 dB, right? Or if you say 15 dB to 8 dB, that's 7 decibels of loss. It's only 5.5 kilometers, whereas 7 decibels is supposed to give me 35 kilometers, or you can see out here it's supposed to be 33 kilometers. So instead of getting 33 kilometers, I'm getting only 5.5 kilometers, and that is a practical problem with how these fibers are in our metro areas. Despite that, we are now trying to connect Chennai to Bangalore, which is on fiber about 550 kilometers. This 550 kilometers has stations at about 30 to 50 kilometers away, wherever we have these white circles. And we are trying to ensure that we are able to transfer the key from Chennai to Bangalore, and so connect, for example, maybe two offices of the same company across these two cities. We could also connect them at branch offices, let's say at Vellore, Krishnagiri, and so on. So these are happening today as we speak. We are looking at the fiber, we are monitoring the loss, trying to understand how that is coming. The QKD boxes looks like these what are called 3U 19-inch rack mountable boxes, and inside them there is a plan for us to put these photonic integrated circuits to reduce the cost of them. After you do that, you then still have to go from Bangalore to Delhi. So you remember the Chinese one, which was 2,000 kilometers. We have a similar plan here that will take us from Bangalore to Delhi, about 2,500 kilometers. And we'll have secure nodes every 100 kilometers. Some people will say they can do 500 kilometers. And yes, no one is denying that they can do 500 kilometers. The problem is this: if you go to anything more than 100 kilometers, your rate drops. So you have to actually keep worrying about the secure key rate. And if you don't have any specification on that, then you can do whatever distance you want. So if you look at all the networks that are being built, and I like this table because it gives me an understanding of what people are talking about. If you notice that some networks, like the one in Cambridge, UK, has been running for 2 years, whereas somebody is running it for 1 day. So everybody publishes something, but we have to be careful when we read this, because something that is running for 600 days has more stability than something that is running for 180 minutes. This is like 3 hours. So 1 day, 3 hours, even 25 days don't actually tell me that this network is stable. And you can also look at the loss associated with some of these links. This is only 5.6 decibels, right? Whereas some others have 3.9 or 30 decibels. So 30 decibels loss is much higher than 5.6 or 2 decibels loss. So comparing these different networks requires a little bit of technical understanding. And again, you'll see that everybody has got kilobits per second, secure bit rates, except this one where they have got megabits per second. They have a special detector which has allowed them to multiply by 10. And we think it's just 10 parallel detectors that are multiplexed to give us this higher key rate, right? This last column is what we do. We have got 5.6 and 4.8 kilometers of fiber. The equivalent losses are here. So 7.5 decibels is about 30 kilometers, 3.5 decibels is about 15 kilometers. It has a kilobit per second and it's been running for about 7 months now. So these networks are all in reality, and we have them running in India also. There are a few more ideas that we are playing with. One of them is, instead of using these kind of three pulse things, can we get rid of these three pulse and two pulse and instead just use one optical pulse but put a phase modulation in the middle out here? So instead of using 1 nanosecond pulse, we use a 3 nanosecond optical pulse and put a 1 nanosecond phase. And that automatically gives me the three paths, the ABC paths are now A, B, and C. And it turns out that this sort of experiment was also possible, and my student Gautam showed that we can do something very simple. Why is this interesting? Because we can now do it on a chip. So this is the path that we are talking about. Let's say this is B and the top side is A. And here you have an intensity modulator. Here you have your phase modulator. Here you have an attenuator. And on this side you have another A and B, which forms the detector side of things. So you can actually build a chip which has both the transmitter and the receiver, and both of them will have good performances. This chip is now getting packaged. It will come out in a small little form factor. But again, everyone thinks these are photonic integrated circuits is where the work is, but actually there's a lot of work in the electronic integrated circuit. So this electronic integrated circuit needed its own design, its own fabrication, and the two devices will then get co-packaged into this small little package that is here. So there are many protocols. I showed you one called BPS. There is another one called plug and play. This was actually demonstrated in 2002. Nothing is ever plug and play, right? What we've discovered is, as we try to implement these things, these are all very complicated experiments, and even the plug and play system is imagining that the quantum channel does not vary in time faster than the time it takes for the photon to go from Bob to Alice and back to Bob. So in this particular scheme, you'll see the lasers on the right. It goes through, picks up a phase out here, goes through the quantum channel, goes through some delay lines, hits the phase modulator, hits a Faraday mirror that corrects for any phase fluctuations, and then sends it back. So the assumption out here is that the phase fluctuations on the backward journey are the same as the phase fluctuations on the forward journey. So if the phase fluctuations are slow, then you can correct for it. But if they are fast, then you can't correct for it. Right? And here is what I was telling you about the crosstalk between the two fibers. You will notice that I'm sending on the classical channel something that is a 16 nanosecond periodicity. I'm picking it up on the quantum channel just because the two fibers are next to each other. So what are the technology needs that for building such quantum networks? First of all, as I've already mentioned, we need interoperable equipment. We also need to worry about size, weight, power, and cost, what is called swap plus C. Sources of photons, detectors, electronics, and you notice all of this is classical. Although we keep talking quantum, actually we are doing a lot of classical work, right? Even this software out here, which manages the key, is developed by CDAC Trivandrum. It's of course classical, right? Fibers are classical, packaging is classical. The quantum aspects of it are fairly limited. I would think maybe 10 to 15% of a network. The team itself is always interdisciplinary. So you notice out here, we have theorists and experimentalists. So it's not just physicists. And I think that's another mistake that we make. We think physics, we need a lot of physics. No, we actually need a lot of communication engineers. We need technicians. And that is how we've been building it out. If you look at what we are doing, we are building hardware using microcontrollers, using lasers, using detectors, modulators. So sources, detectors, all these hardware builds are required. And then all these networks are all classical networks that are working on regular fiber optics. So now the collaboration is joined by IIC, IIT Hyderabad and IIT Indore on Killa. The hub itself does a little more things. The hub has C.Delhi that does post quantum cryptography. It has IIT Delhi that does entanglement distribution at Delhi. It has RRI Bangalore that is doing quantum repeaters. It has SAC ISRO that is trying to put up the satellite based QKD. All these aspects come under the quantum communications hub. So if you look at the hub, it's called IITMC Samya Technology Foundation. It has these technical groups. It has 23 member institutes. It is talking to a lot of the startups. It is talking to a lot of the companies themselves. So this industry, academia, research lab collaboration forms the basis of the hub. Right? So I've spoken for about 45 minutes. Let me stop and take questions. I will end my presentation with one slide, which I like to always say. Physicist David Deutsch said computers are physical objects and computations are physical processes. What computers can or cannot compute is determined by the laws of physics and not by maths. So a lot of people think that I need to learn a lot of maths in order to do work in this field, which is true. You need some people who can do the maths. We need a lot of engineers who can build things. So I say you believe in physics but rely on engineering. What that allows you to do is to build good experiments. High speed experiment, high speed electronics, RF electronics. That's what you need. You believe in the physics because every so often the experiment will not give you the results that you want. And it's not because there is anything magical out there. The physics will work. It is just that the engineering is not being done to the extent that it should be done. So if we focus on the engineering, then the experiments start work. So let me stop here and take questions. Are there questions in the chat box? Is that where we look for it?
Yes, sir. The questions are in the chat. I'll just look up. I can read it out for you, sir.
Yeah, please do.
Nandaji, I'll call you in just 1 minute.
Okay. Okay.
On commission. Sir, mostly there are no questions. There is one question which says quantum layer has set some standards to work. Yeah, I think that's a comment also. Yeah, participants, if you have any questions on the lecture, especially, I hope the lecture is very clear, and then, yeah. Anything that you would like to ask or anything that you want to find out, you are most open.
Yeah, so there's one question that says explain quantum communication for free space and satellite. Yeah, so if you look at, maybe I'll share my screen here again. Give me a second. Okay. Not yet.
Sir, you can navigate somewhere. We can see your screen now. We can see your screen, sir.
Yeah, now you can see my screen, right? Yeah, okay.
Yes, sir. Yes.
So in free space, what we are trying to do is something very simple. All we are trying to do in free space is you have a laser. Sorry, and the laser beam is being sent out, and here you have a lens which focuses it down onto a detector. Now, light has a property that it could be polarized, and typically we'll say it is horizontal or vertically polarized. We can also say use any other angles, and we say it can be polarized along the 45 or 135 angle, right? So these are the two angles, 45 or 135 degrees. So if I want to send a 1 bit, I send it on the vertical polarization. If I want to send a 0 bit, I send it on horizontal polarization. Similarly, out here, if I want to send a 1 bit, I send it at 45 degree. And if I want to send a 0 bit, oh sorry, I will do the other way around. I do a 135 out here, and 0 bit, I will send it at 45 degrees. Now, what I've done is that I have two random number sequences. So random number generator 1 is giving me my bits, and random number generator 2 is giving me my basis. What is basis? It is either this plus basis or it is this cross basis. While in a digital sequence, we are only having one bit of information on every time bin. So we are saying 1 and 0. Here, we have broken that information into the bit value and the basis set. So we transfer this in two different parts. And so an eavesdropper is not able to capture all of it. So the experiment is very simple. All you really need out here is a polarization controller. That allows you to transmit it either along the plus or the cross basis, and allows you to pick up the bit value, and based on the bit value, it's either vertical or horizontal, or it is 135 or 45. The detector side also, you're making the same choice of either plus or cross basis, and then you detect it. Now, if your plus on the transmit side corresponds to the plus on the receive side, then you'll detect it successfully. If, however, on the transmit side, let's say you chose plus, and on the receiver side you had a cross, then you detect it only with 50% probability. Right. Similarly, if I had a cross out here and a plus out here, then I get it with 50% probability out here. But if I had a cross out here, then I'll get it exactly. So the uncertainty in the choice of basis is where the security comes from. Right. So this is what the transmitted basis is, and this is my receiver basis. So you can show, and this is the very typical what is called the BB84 protocol, because it was presented in 1984. So everybody refers to it. It's a very simple protocol, right? Where you understand that light can be defined in terms of its polarization, and this polarization is what we use to encode and break the information. So you're breaking the information into the bit value and the basis set, right? So you have two random number generators instead of just one. At the other side, they also have only one random number generator because they will choose the basis, right? This is at the detector side or the receiver. But the bit value is then random half the time, right? And that is where we can derive the security from. I hope that helps. Well, there is no real difference between free space and satellite. Satellite is you're doing this from a satellite and you're sending it down to Earth. Free space is you're doing it from 2 points on Earth. There are many other questions. Let me see. Most equipment is classical. How is this quantum technology and communication? Yeah, so unless you use some of the properties of light that make it quantum, it is all classical communication. So the quantum parts of it come when you have a quantum source, a quantum emitter, when you have a single photon detector. But remember that you have to turn on the source and turn it off, and that is done electrically. Similarly, detector, after it detects, it generates an electrical signal that you measure. Even it's not really quantum key distribution. My colleagues have taught me that this is a bad name. It's not really quantum key distribution. This is wrong. What it is a classical key distributed using the quantum properties of light. So this quantum key distribution is just a short form. The true definition is classical key distributed using quantum properties of light. Why is that? Because your key is a bit string, no? So I can read it. It's a bit string. It's completely classical. Even this BB84 protocol where I'm saying a photon can be polarized and all, if it's one photon, to do that I have to get a quantum source. So quantum source is usually a quantum emitter, or it is called a single spontaneous parametric down conversion, or what is called an SPDC, right? Sometimes people will say the quantum source is a squeeze light source. This is like all very, a course in quantum optics, right? How do you build all of these? And then you have the single photon detectors, which again, detectors, which again one has to ask, right? How do you make it? Well, you use a photodetector. So this is a classical device. You feed, you build a circuit like looks like this, some bias voltage, some gate voltage, you put some resistor, put an op amp as a comparator. If you're an electrical engineer, you do all these things as part of what you normally do. So if you build a circuit, then the output out here is a pulse every time there's a photon that comes in. So this single photon detector is detecting the arrival of a photon, but is generating a classical pulse. So this pulse out here becomes a 1 bit, right? Classical bit. So how do we say it's quantum? Is because we are relying on some of these quantum optics definitions. But the engineering building the network is all classical. How do you explain quantum communication layer and quantum layer interactions? Okay. So let's say there's a QKD layer out here. So there's a transmitter and a receiver, both in the QKD layer. So these people generate some key. Now this key has to then go to the classical layer where you have the encryptor and you have the decryptor. So this key is transferred over on both sides. So this is a Q key, right? It's actually a classical key. This is, remember, this is the key. It's some random number generator that has generated these bits, and that is being shared equally between the two sides, the transmitter and the receiver. Once both of them have this, then this key is used here, and a copy of it, which is available on this side, is used out here, right? So the same key gets used on both sides, so that you have the encryptor and the descriptor. And let me change the diagram a little bit. Encryptor and decryptor, and here you have this classical, what is called a ciphertext. This is your ciphertext, right? So this key is used to encrypt and decrypt. So that's the primary difference. So in a network, what we are doing is, okay, I have one node. So this is one QKD node. I have another node, and we are connecting them together in some form. And then we have a classical layer out here where the keys are sent. And so you have the encryptor and the decryptor on the classical. This is what we are calling the QKD network. So this entire thing is a QKD network. What are the benefits of a quantum mission? The benefits are we encourage startups to look at the technology. We encourage faculty, students to get trained in the technology. We encourage more programs, more interactions, more collaborations. So, right now we have 50 universities who are talking to each other. That's part of the mission, right? To get the energy into the space and ensure that we stay ahead of the technology as more developments come up. In terms of quantum communications, we are doing quite fine. I think India needs to do more in terms of quantum computing. Quantum sensing is a little bit in the middle. We can do better, but we are not far behind. Can PQC guarantee safety forever? No, because PQC at this point does not have a security proof to say that it is unconditionally secure. It only says that we hope that it cannot be broken on a quantum computer because there's no algorithm. But if there comes around an algorithm, then it cannot guarantee the safety. You have to change the algorithm. If QKD is based on physics, is it 100% unbreakable? Let me write that question down. Is QKD 100% unbreakable? The answer is a big no. Okay. Why is that? The one-time pad, oops, is unbreakable. Remember, I had that example. I take a text, I take my key, and I XOR it. So I end up with a ciphertext. And this is my plain text. What is my ciphertext? XOR is gives me 1, gives me 1, gives me 0, gives me 1, gives me 1, gives me 0. I transmit this ciphertext and I have 110, 110. If I have my key, which is the same key out here, then I should recover my plain text. And you can do that very quickly by doing the XOR operation. 1, 0 gives me 1, 1, 1 gives me 0, 0, 1 gives me 1, 1, 0 gives me 1, 1, 1 gives me 0, 0, 0 gives me 0. So now you compare this text with this text and both are the same. So the one-time pad, OTP out here is one-time pad, not one-time password. The OTP out here needs number of key bits equal to number of plain text bits. But remember, in quantum key distribution, what I showed you was that my secure key rate is about 1 kilobit per second. My data transmission rate is about 1 gigabit per second. In simple terms, what I'm doing is I'm reusing the same password or using the same key 1,000,000 times, right? Kilobits per second is 10 to the power 3. Gigabits per second is 10 to the power 9. Well, if it's a 1,000-bit key, then it's not 1 million times, it's 1,000 times. Right? 1,000 and 1,000 gives me 1 million. 10 to the power 3 into 10 to the power 6. 1,000 into 1,000 will give me 10 to the power 9. Right? So here in OTP, I need them to be equal. Whereas here, if I use a 1,000-bit key, I have to use it 1,000 times in order to get the same data rate. So it is not unconditionally secure in a practical implementation unless I make it unconditionally secure, right? By slowing down the data rate. Can we explain the significance of Shannon entropy in quantum communications? Well, so Shannon entropy is just the carrying capacity of a communication channel. Now, there is a problem in using this definition without fully thinking about it. So typically, it is something like P log P, where P is a probability, right? For classical channels, this works very well because the probability, when you transmit a bit, you can receive a bit. The probability to that is 1. So this is actually the error probability. In a quantum channel, this does not work very well because if I transmit a bit, if I transmit 100 bits, what I receive is only 1 bit, right? So I can't really use the classical definitions the way that they use it in classical communications. I have to always work with what I received out here and then calculate the error on this before I put it into that, right? So you'll find that we normally use E log E, where E is the error. But the errors are defined not on the transmitted bits, but on the received bits. So this is where the quantum bit error rate comes in, right? Why? What is the difference between bit error rate? Bit error rate in a classical communication channel is number of received errors divided by total transmitted bits. The assumption here is the total number of received bits is equal to the total number of transmitted bits. In the quantum bit error rate, we are doing something else. We are saying number of received bits in error divided by total number of received bits. Because you remember that picture I showed you, the loss is like this, right? So, well, maybe I didn't show it to you. So if we look at the power that is transmitted or received versus distance in kilometers, it keeps decreasing exponentially. It's e power minus alpha x. What is this alpha? This alpha is 0.2 decibels per kilometer. Right? So 100 kilometers, 20 decibels, which means I transmit 100 photons, I receive 1 photon. So if I put this definition out here, then on the denominator I will get 100. And my QBER is very small, it is not representative. Whereas in the denominator, if I put 1 and that is an error, then I get 100% bit error, right? So we use for quantum channel, we use this as the error. And then we stick it into the same type of formula, it will look like E log E. So the entropy formulas are a little modified from the classical entropy formulas. Okay, I think I've run out of time. So I won't be able to take all the questions. I don't know if there are many more, but I seem to have covered most of them. How to prepare a
Yes, sir. I
security
think
key for a given encryption? I'm not sure I know the answer to that. Yeah. All right. So let me stop sharing screen here.
Yeah, Dr. Venkat Subramaniam sir also has joined. Thank you, sir. Welcome, welcome for joining for today's session. We have two great
Thank you very
individuals today
much.
here. Yeah, and thank you very much, sir.
Apologize. I think clearly I needed more time if I looked at all the questions, but I did the best I could. So hopefully people can
Right,
connect
right,
with
right.
me if they have more questions, right? All right.
Yes,
Thank you
yes.
very much.
Sure, sir. Thank you. Thank you so much, sir, for your valuable time and being here. And yeah, yeah, I think now we have another great individual with us here. It's Dr. L. Venkat Subramaniam. He is the IBM India quantum lead. So for anything that is happening in IBM regarding to quantum, especially at the Indian country level, sir is the responsible person. Sir did his BTech from PES College of Engineering, Mandya, then MS in Electrical Engineering from Washington University in St. Louis, USA. And then he came back and did his PhD from IIT Delhi. And since then, he's been with IBM last 27 years. That's a remarkable feat. And sir has authored a book called Quantum Nation. And that is very remarkable because it has been translated into many languages. And for all of us sitting here who understand Telugu, the book is available in Telugu also. It has been translated to Telugu. So you can understand the importance. Please get a copy of it and try to take it forward. And without wasting much of time of Venkat sir, I will request him to take it forward. If you understand the program that is being held, and if you have enjoyed the last 20 days, various sessions that have been conducted, MNIT has been doing various sessions for facilitating AICT syllabus with along with NQM, National Quantum Mission. The brain behind it, I would say, is Dr. L. Venkat Subramaniam, and that is where he is. And he's been he has also been guiding AP State Council for Higher Education, and this program is also specifically aligned with that. Anil sir is also there from AP State
Sir,
Council for Higher Education.
sir, good
Yeah.
afternoon and welcome, sir. You're the most
Thank you, sir.
sought
Thank you.
after, sought after man in the quantum nation. Welcome,
Yes.
sir.
Yeah, thank you so much. And then, yeah, the dream of Venkat sir is that our country should become a quantum nation. And I request him to share his thoughts and vision. And then hopefully in the next few courses also, sir will join and share some insights. But today, let us listen to him. Next 1 hour, it's Venkat sir with us. Over to you, sir. Thank you so much.
Thank you, sir. It's a pleasure to be here with everyone, and I must thank Pilli sir for the amazing work that he and the team have done. Actually, this is the second time they are running this course. They ran it in at a national scale. You know, I remember, yes, as he said, we started out, earlier. And yes, we were discussing, but I never knew that he is going to be able to pull it off at this scale. Okay, once he started, there was no stopping, and it has been an amazing journey. And I really am very happy that so many faculty have been reached through this program. And in Andhra Pradesh, it's great because you have a beautiful opportunity in Andhra Pradesh, especially because of the kind of backing that the state government is giving at this point. And in fact, they are the people who brought Pilli sir all the way from Jaipur to deliver this course in Andhra Pradesh. So, and I know he went in the beginning, you even traveled, right, to deliver the initial
Yeah,
sessions in
Amravati, we have been there. Yes.
Yes. So it's a great journey, but it is only the beginning. Okay, so I know you've already gone through 20 days of studies. Okay,
Yes.
so here I hope people can ask questions in between. Okay, so we would like all of you to have an interactive session. This session here is not going to be a technical one. In fact, I'm going to focus more on what you have learned and where we think that you can apply your learning. Okay, so that's what we are really thinking about here in this 1 hour. Okay, to talk about things that you have learned and how you are going to take it to your students and what are you going to do with this learning, because that's the most important part. It is great you have all learned things, but what are you going to do with this learning is even more important. That's a question we all have to answer together. Okay, so I'm going to start presenting some share screen, my screen here. Just give me a second. Yeah. Okay. So I hope you can see my screen. Yes. Good.
Yes, sir.
Okay,
Yeah.
sir.
Yes,
Yeah.
sir. Okay.
This. Okay. So now the first question, I hope you can all type into your into the chat window, or you can please feel free
Yeah.
to unmute yourself and
Yeah.
talk if you like. Yeah.
Yeah, participants, you can use the chat and keep typing. Sir will be
Yeah.
looking at that, and then he'll be able to answer your queries as well. Of course, in between, we may also pause, sir, to say that some questions are there in the chat, right?
Yeah.
So please use the chat box, and otherwise, rest of them are on mute, sir. So we will
Okay.
continue
Okay.
to, we
Fine.
will keep
Let us
asking,
use.
and then you
Sure.
can take it
Let's
forward.
use the
Thank you. Thank you
chat.
so much.
Thank you, sir. Okay. Perfect. So we are going to use the chat window here. So the first question that I'm going to ask you is, okay, how do you program a quantum computer? Okay, so you want to use a quantum computer to run your programs. Okay, so what is the programming language? How are you going to program it? So that's the question. Please type in the chat window the answer to this question as to what you think is a programming language. Okay, excellent. Somebody said Qiskit. Now, is Qiskit? Yes, Python, excellent. Qiskit is a Python library that people use. Okay, so Qiskit is Python basically. Okay, so is that a higher deep learning? Okay, deep learning is not a programming language. Okay, so we are talking about the programming language that you can use. So is Qiskit or Python a higher level language, or is it a machine language? Okay, it's a higher level language, right? So the programming language for a quantum computer, hence, is the same as what you use for programming a classical computer. Okay, so classical computer, your laptop basically, or any supercomputer, you can use Python for programming. Same way for a quantum computer also, you can use Python or a Qiskit as it is called. Qiskit library, which is the software development kit written in Python, which you can use for programming a quantum computer. Now, in a classical computer, once you write your higher level language, there is something called a compiler. What does the compiler do? What does the compiler do for taking your higher level language and converting it into, translate into machine level language? Excellent. So somebody has said that the compiler's job is to take your higher level language, which is Python or Qiskit or whatever, and convert it into a machine code. Now, the classical processor on your mobile phone or on your laptop is what? What is the machine language that it converts it into? What is the machine language for your Intel processor or for your, yes, it's a binary language. So your, program gets compiled into machine code, and that machine code is then run on the processor. And that processor contains bits as the fundamental unit of information. Zeros and ones are the fundamental unit of information on your classical computer, which has bits. Now, on a quantum computer, the same higher level language, remember Python or Qiskit, now that Qiskit gets compiled or transpiled into what is the machine language for a quantum computer. Yes, so that gets translated into qubits, okay? So for your quantum computer, your machine code basically is a series of qubits, which is where the processing is done. And these qubits, in fact, you are converting your, the technical language, you can say, in your technical language, you can say that your higher level language gets converted into a series of circuits. And what are these circuits? These circuits are qubits and operations on multiple qubits through your gates. So the programming language converts your machine into a machine code comprising of qubits and operations on these qubits. Okay, so that is what is happening, right? So we just saw that the difference between a classical and the quantum computer is not in the way you write your program, which still remains, Pythonic, but what is happening at the back end is where the difference is. Okay, so the qubit is what your processing units are on the quantum computer, and that's what you are targeting as through your program. Now, you might all have, very briefly, I will just say that there are a certain class of problems that only can be solved on a quantum computer, but not even on the best supercomputers. Okay, the best supercomputers also cannot solve certain problems. So some of these include things like simulating molecules and chemical reactions. Okay, if you wanted to simulate molecules and chemical reactions, so for example, if you wanted to simulate the caffeine molecule for a single fraction of a second, for a single instance, how are the molecules placed? What are the energy configurations of the subatomic particles inside of the molecule? If you wanted to do that on a classical computer, you would need 10 to the power 48 bits to represent the energy configuration of a single caffeine molecule at a single instant on a classical computer. 10 to the power 48 equal to 10% of the total number of atoms on Earth. And we don't have a classical computer that big. So today, molecular simulation of even small molecules is not possible even on the best supercomputers. For molecules like caffeine, it is not possible to simulate these molecules even on the best supercomputer. On a quantum computer, it is shown that all you require are 160 logical qubits. But do we have 160 logical qubits yet? Unfortunately, not yet. But it is not very far before we have this. Okay, in the next few years, we are going to reach this point, and hence at that point, we will be able to completely represent the molecular caffeine configuration of caffeine on a quantum computer with 160 qubits. Okay, so that future is coming. It is not yet there, but it is coming, right? The other problem, in the previous lecture, people, sir talked about communication, encryption, and coding. Does anyone know which year did Shor come up with the Shor's algorithm? In which year was the Shor's algorithm discovered? Anybody wants to type? 1994. Yes, ma'am. Dr. P.V. Rajeshwari. Yes. So Shor's algorithm was discovered in the year 1994. And what does Shor's algorithm say? Shor's algorithm finds a way of factorizing large numbers efficiently. Why is this important? Where is factorization used? So today, all your passwords, this call, even if somebody were to tap into the signals of this call, somebody sitting outside this room says that, oh, I'm going to hack into this Wi-Fi signal and I'm going to see what all strings of information are being transmitted. If they were to do that, they will not be able to listen to our conversation. Why? Because that would be encrypted and encrypted using RSA encryption. Okay, I see a question. Let me just read it. Oh my God, this is a very long question. Sir, if possible, kindly guide us by providing information on the different vendors available in India whom we may approach for procuring equipment to establish quantum laboratories. Yes, please contact Pilli sir after this call, and I will have shared information on where you can obtain information for setting up labs. Okay, so I will do that. I've not read the rest of your thing because it's very long. So now, so what is prime factorization? You take two numbers. What are the prime factors of 15? 3 into 5, because 3 and 5 are both prime numbers. What are the prime factors of 100? 2 into 5 into 2 into 5, because 2 and 5 are both prime numbers. But if you take a very large number and say that give me the prime numbers of this large number, a 2048-bit integer, if I start with that and I ask you to give me the prime factors of that large number, it is going to take you 6 billion years, billion with a billion years, longer than the duration of Earth so far. Okay. So do we have a supercomputer that can break it? No, we don't have. And that's the reason why we take large prime numbers as our keys today, multiply it and use that as the encryptor, okay, for our information today, okay? So, but Shor in the year 1994 showed that you can find this prime factor, which takes 6 to 8 billion years on a classical computer in a few hours, like 8 hours, exponential speed up, okay, compared to what you can do on a classical computer to what you can do on a quantum computer. Exponential speed up in terms of the time that you can do it. No, we cannot run Shor's algorithm on a classical computer. If we were able to, then we will say that we are already done. Yes, you can run Shor's algorithm on a classical computer for small numbers. But for small numbers, you can also run it on your classical computer. You don't need a quantum computer to run it. Do we have quantum computers big enough to run Shor's algorithm for large prime numbers, 2048 bits? No, not yet, but that is also coming in the future. Just like I showed you that, this problem of computing caffeine, states, you can do it 160 qubits. Similarly, you can do Shor's algorithm if you have sufficient number of qubits, which we don't have yet. So Shor's algorithm, yes, mathematically it showed that you can run it and you will be able to break RSA encryption because you can find these prime numbers, but you can only do it when you have a large enough quantum computer with you. Okay, so not yet, not yet. So what is the other problem? So who can define AI here? What is AI? This is a very important question. Can we run Shor's algorithm on a quantum computer, on a classical computer? The answer is no. Why? Because classical computers use bits and bits have their limitations. Yes, please, what is artificial intelligence? Can somebody define it in a few words? So the question is, please define artificial intelligence. What does it mean that a system has artificial intelligence in it? When somebody says, my system has artificial intelligence, what does it mean? Human intelligence on a computer, making computer to think. It basically means that I can learn from examples because that's what you do. Okay. You learn from examples. Like when you were a child, somebody said, here is a cat. So you saw one cat, you saw another cat, maybe two cats, and then the third cat comes and you said, Mummy, cat. So you learned from examples. Same way, artificial intelligence is also about learning from examples. Okay, that's what artificial intelligence is. Any intelligence takes data as input, learns from that data, and gives decisions as output. So as a child, your mother would have shown you cat, dog, cow, lion, all those things. And then you learned from those examples. They showed you pictures, they showed you sounds maybe of how the cat does its meow and how the dog barks, bow, bow, like that. So all of these are inputs to your brain, and from that you are coming to learn about things. Okay, so cat is an example of something that your intelligence in your brain learned that this is a cat. Now, artificial intelligence, the same cat, the AI can also learn, but how many cats does AI need to see before it learns cat? You, human, required one cat, maybe two cats to learn cat. But how many cats does AI need to see before AI can learn that this is a cat? Has anybody here built a AI system? 1,000, yes. So it in fact needs more than 1,000. It needs thousands of cats where it is looking at cat examples, because if you just give it one cat, then the AI is going to confuse cat with dog, with lion, with a piece of cake, which looks like a cat. All of these things, the AI will say cat. Okay. So there is a problem here that today's AI uses lots and lots of examples to learn from. And that also means that AI today is very inefficient. It eats more power than is required. Your intelligence system needs dosa, idli, all of that. That's it. And we are done. We eat that in the morning and our AI or our intelligence starts working. Okay. That's all the power it needs. But AI systems need huge power, lots and lots and lots of power. Why? Because their learning is not as efficient as ours. We can learn cat from one example, whereas AI requires thousands of cats to learn from. and which means that AI also requires lots and lots of power compared to, 2 rotis for you versus 10,000 or whatever, thousands of rotis for the AI system in the form of power that it consumes. So we have now seen three problems. One is molecular simulation. The second one is the problem of factorizing large numbers efficiently. And the third problem we have seen is the learning problem. In all of these three, we are seeing that quantum computers are more efficient, at least mathematically so far. And it is expected that as the number of qubits keeps going up, we are going to see large efficiencies in these systems. We are going to see these quantum computers be able to solve these problems which classical computers are very inefficient at, or in fact cannot even solve. So for example, if you look at the caffeine molecule, if the classical computer was to try even, it is not going to succeed because it's very, very unlikely that you are ever going to have a supercomputer with 10 to the power 48 bits to represent the energy configuration. So you might as well forget it. We also know that, for example, for factorization of large numbers, it takes billions of years on the best supercomputer. So you can forget it. Okay. Learning, yes, we are doing a lot of learning tasks today. We all use ChatGPT. Okay. We all use DALI and all these programs for AI, which is good. But a lot of this is very inefficient. It eats up a lot and lots of power. So again, quantum is expected to help us here to reduce and make AI more efficient. Okay. So, but does this mean that quantum computers are good at everything? No, it does not mean that. Classical computers are still good. So for example, you try to do multiplication, you can do multiplication much faster on a classical computer compared to a quantum computer, hundreds of times faster. So there are tasks on which classical computers are better than quantum computers. So quantum computers are not going to replace, they are not going to replace classical computers. Classical computers will remain in this world because they are useful also for several tasks, starting with multiplication. Okay. But of course, as we saw, bits have their limitations, and that's why we have brought in qubits. And over the past 20 days, I hope you have learned about superposition, entanglement, interference, which are the properties which make the quantum computer special, which is what enables us to solve things like Shor's algorithm, which enables us to do molecular simulation, which enables us to do better, representation and inferencing for machine learning tasks. So these are some of the things which enable, these are the quantum mechanical properties which enable a quantum computer to do well on certain kinds of tasks. But as I said, in future, classical computers, which are well suited for many problems like multiplication, will continue to be there, but quantum computers are going to unlock classically untractable problems, problems which cannot be solved using classical computers. You will solve them using quantum computers. So in future, you are going to have CPU, GPU, and QPU working together. The three are going to work together. All three will be accessible. Today, CPU is sitting on your mobile phone, on your laptop, and all of that. Usually GPUs, yes, there are some laptops which have GPUs on them, but often GPUs are sitting inside data centers, and so are QPUs. QPUs are also sitting inside data centers, at this point of time. So both QPU, CPU sitting in data centers, CPU sitting on your laptop or on your mobile phone. And these three together lead to what is called quantum centric supercomputing. So you're going to solve bigger and bigger problems using your laptop, but often a lot of that program. So for example, today, the chat GPT is actually running in a data center in a server somewhere. Okay, so that's what is happening. It's running on GPUs. But on your local processor, the CPU, there are several things running on your CPU also, of course. So there is this happening where CPUs, GPUs, and QPUs are already working together. Okay, so already these processors today work together. Now, just like Moore's law, does anybody know what is Moore's law? Please type what is Moore's law. Yeah, anybody Moore's law? Yes, you can check. It's an open book exam, so you can check. Yes, number of transistors double every 2 years or 18 months. So 18 to 24 months, the number of basically your processing power doubles. That's the reason why all of us start going and buying mobile phones every few years, because why there is a new camera, faster processing, better apps can be run on your system. So all of these things mean that your as you pack more and more ICs onto your transistors, it is meaning that you are also able to double your performance almost every 18 to 24 months. Same size laptop, but it becomes more powerful. And that is why we all have to go and buy, your old laptop starts becoming slower and slower. Why? Because there are new apps which are running on it, and those apps expect a faster processor. They expect more. Okay, so that's why your mobile phone, every new mobile phone launch has a more powerful processor sitting inside. Okay, which means better camera, better games, better kinds of apps which are running on your classical computer. But same way, we are also observing that quantum computers are also doubling in their performance almost every year. Okay, 2016, 5 qubits, 2025, 156 qubits. And by the year 2033, we expect that there are going to be almost 1 lakh qubits, okay, working for us. Okay, so which means that quantum computers have also been increasing in their power very, very quickly. And that means they are going to be able to, solve bigger and bigger and bigger problems. And in fact, by the year 2029, we expect that quantum computers will be error corrected. So you will have error-free qubits available to you by the year 2029, which is not very far away. In fact, the students who are entering in their first year now will be graduating when error corrected qubits will be just around the corner. Okay, so error corrected qubits coming out within the next 4 years. And so this means that yes. So the question is, sir, can a data scientist do quantum computing? Yes, anybody can do quantum computing. In fact, it's a great idea for data scientists, those who are working on AI, optimization, any problem that you are working on today, you are using classical methods. Please do the same on a quantum computer using quantum methods. Okay. The role of a mathematics teacher or in which direction they work. Excellent. So I'm going to also tell you what a mathematics teacher should be doing. The fundamental basis for all of this is linear algebra. Okay. So you might have heard about the new courses that AICT has, started. You are all, in fact, here in this FDP program to start teaching those fundamental courses, QT1, QT2, QT3, and all of that. Why is a mathematics person needed? In fact, the basis for all of this, for all this quantum mechanics, for running your programs, for solving these problems is linear algebra. Linear algebra is the basic thing that everybody needs to learn quantum mechanics and to learn quantum computing. And this is a very important question. The mathematics teachers, Dr. Haimavanti Talla, it's very important that mathematics foundation is laid for our students, for our faculty. In fact, I would urge you to start looking at what is the basic linear algebra, which is required by anybody to start learning quantum mechanics or quantum computing. And so please, as a mathematics teacher, please just focus on teaching people enough linear algebra, and it should not take more than a month to learn that basic linear algebra. Teach that, and I think students and faculty and everybody is all set to jump into this journey to learn quantum mechanics. Okay. So 2029 is a very important milestone. The other milestone is quantum advantage, which is happening in the year 2026. This is the year 2025. 2026 quantum advantage. What is quantum advantage? Quantum advantage is to demonstrate that a quantum computer can solve a problem which is useful. Okay, useful. It can be a business problem or a science problem, and you solve it on a quantum computer much, much more efficiently compared to a classical computer. So somebody just asked, can a data science person, data scientist can do quantum computing? Please take your data science problem, run it on the quantum computer. And if you can show that on the quantum computer, you are able to solve a data science problem much more efficiently compared to a quantum computer, that means you have achieved, compared to a classical computer, that means you have achieved quantum advantage. Okay. So in fact, that's something we want all of you to focus on, to take classical algorithms, rewrite them as quantum algorithms, run them on quantum computers, and use that to solve a problem using quantum computers. Which quantum algorithm are closest to real world deployment in life sciences? That's a very good question. So one of the problems which I showed you, which was about molecular simulation, energy states, and things like that. In life sciences, a lot of things like protein folding, a lot of things like binding energies of two molecules, how do they work together? And this question is a very good question. What about biology teachers? So biology is the basis for nature. Okay, basis for nature. How do two molecules interact with each other? What is photosynthesis? How does it happen inside the leaf? What kind of processes? How are the proteins involved in that? And quantum computing is supposed to model these things only. Okay, so Captain Dr. Y. Polly Naidu, it's very, very important. Your question is very important. Biology needs to be the first area. In fact, it is the first area where people are studying how molecules and substances within the body, things like proteins, are interacting with each other. In fact, your question brings me to this problem here, which is protein structure prediction. problem which IIT Madras and IBM people worked together on. So this was to predict how proteins have, given a, amino acid chain or whatever, what kind of shape is that protein going to take? So that prediction, I don't know how many of you know, but last year's Nobel Prize in Physics was for AI people, but the Nobel Prize in Chemistry was also for AI, for basically for protein structure prediction. How can we play a role in Amravati Quantum Valley? How can we get access to learn? So first of all, I want each one of you to know that, okay, where is that? Okay. If you go to IBM Quantum, you can get access to a quantum computer, okay? So you please, if you have not already gotten access to a quantum computer, please do this. You can also run programs on a simulator on your laptop. Okay, you can download Qiskit on your laptop and use your laptop as a quantum simulator, and you can run up to 15-20 qubits on your laptop itself. Okay, so please do this. Number one, use this IBM quantum system. Number two, if you don't want to use this system, download Qiskit on your laptop. Again, Dr. Pilli will share the details of how you can do this, okay, on your laptop. He will share instructions for you. So please start running this, okay. Amravati Quantum Valley is going to get the most powerful quantum computer very soon. The IBM and TCS are coming together. But each one of you should right now, before that comes, should be using these, resources which are available for you for free. Okay. So 10 minutes of QPU time every month is available for you for free. So please get this access, start running programs on quantum computers. If you don't know programming, don't worry. Take your students, they know programming. Talk to them to simulate. Like say you're a physics faculty or you're a biology faculty. Take some of your problems which can be turned into computational problems. Okay. So in high energy physics, there might be some problems where you want to model something or simulate something, or you want to see how the reaction, what kind of states are getting generated there. So for all of this, take your problem and convert it into a computational problem. That computational problem, first try it on your laptop or on your classical computer. See what are the limitations. Why are you able to run it or not able to run it? Then take that same problem and run it on a quantum computer. Ask your students to do this. Take any problem, convert it into a computational problem, and try and then solve it on both classical computer and quantum computer. Both computers simultaneously. Have 4 students, 2 of them are implementing on classical computer, 2 of them are implementing on quantum computer. Every week on Friday, then they come together, they meet, they discuss what are the problems they are facing. And these, as I said, pick any problem that you have in biology, physics, mathematics, whatever problem you like. The goal is to try and implement it on a quantum computer. Okay, so that's the goal. I am asking for premium, sir. See, if you have used up your 10 minutes completely, then please reach out to the AP government. They are arranging more for you. And I will be very, very happy if you have actually used up your 15, your 10 minutes. If you have really used up your 10 minutes, that is Great. That means because any program that I run, typically that gets finished in a few seconds. Okay. In a few seconds, my program is done. So if you are using like 10 minutes already, that's great. You are now a power user, and hats off to you. So great. So please, once you are done, please share what all you have completed using the 10 minutes. And I'm sure the government will then give it to you for, for free. Okay, that's what the AP government wants, that each one of you finishes your 10 minutes quickly and is able to use the uh, premium time. Okay, that's what they want. The premium time will be given to you if you are solving some really important problems which require more than the 10 minutes. So it's very good that you have already finished your 10 minutes time. Is Qiskit 2.0 IBM certification free or paid? I think it is paid, but I don't know why you want this. Is this because you are a industry professional and you are looking for a job? If you are a faculty, you might have seen that the Qiskit 2.0 is quite basic. Okay, so I'm not sure why you need this certification if you are a faculty. Usually faculty have already gone much beyond what is there in the certification. This certification is for beginners who have to learn to use Qiskit. So if you have used this Qiskit and you are a programming, you are a industry person or a software developer, then that is when you need this. And usually in that case, your institute, I mean your company, whether it is TCS, IBM or whoever, will support you with this. Okay. So that's what that certification is for. Government will not support you for this. Okay. Now, so we are soon going to run out of time here. So, I'm going to, ask people to please keep asking more questions, okay? As we go into some more, details in terms of, okay, so there was also this thing, the government has the National Quantum Mission. The government has announced this last 2 years back, in fact, and now the money has begun to be dispersed in 2024. They came out with they launched the hubs and they launched 17, teams were funded. Okay. So these were the teams across the country that got supported by the National Quantum Mission, but this is only the first round. And several other institutes will also get supported as we go further, okay, into this. So many more teams will get supported. So as somebody here said that they are already using up their 10 minutes free time. This was Prasad Babu. Okay, so very good. So once you all reach that level where you are saying that, look, I've finished my 10 minutes, I can solve very complex problems now. That's the time to go to National Quantum Mission. That's the time to go to the State Quantum Mission and say that, look, I'm solving tough problems now and I am able to, okay, I'm able to solve very important problems. And this is something I can do now. Give me more compute power. Okay, so that's what the government is here for. The National Quantum Mission is here for. As you solve tougher and tougher problems. But for the 90% who are still in the beginning stages, please start with simple problems. Simple problems. 4 students, 2 of them solving the same problem using a classical computer, and 2 of your students solving the same problem using quantum computers. Now, I know that in Andhra state, there is the hackathon which is going on. Beautiful effort, excellent effort from APSHI and all the universities there. Thousands of students are participating. They are all learning how to program quantum computers. And now you are doing this FDP. The perfect time for you and those students to come together, where you are now telling them, here is an important problem from biology, from physics, from engineering, from mechanical engineering, whichever branch, and I want to solve this in a computational manner. So it could be optimization, it could be machine learning, it could be molecular simulation, it can be high energy physics, it can be simulating molecules in a biological process. So all of these problems can be computationally solved, and you want to take that problem, two teams, two students each. You can have more students, but two students solving the same problem. You have to do, of course, some research to figure out, how do I solve this problem? Maybe it is some enzyme reaction in the body. Okay. How do I model this enzyme reaction in a computational manner? That much you will have to do, figure out. But that's how, in my team also we work. Okay. So some people are using classical, some people are using quantum, and every week we discuss, how did we solve this problem? What are the inputs coming from the classical side? What are the inputs coming from the quantum side? And then how do we go and solve this? Okay, so that's the important way in which each one of you, which system used in primary particle experiment? Any system. Are you talking about the hardware system? Yes, I mean, so you can use your laptop to simulate some of these, whatever, this, are there funded projects for quantum drug? Yes, the Department of Biotechnology had a call out last month where they were giving crores of rupees to faculty who can do drug design, drug discovery using molecules. Today, what is drug discovery? Drug discovery is take a molecule, take the diseased proteins from your body in a test tube, molecule in a test tube, pour it, see what is happening, then take it to mouse. Mouse is okay. Then you take it to monkey. Monkey is okay. Then you take it to human being at Ames. Human being is okay without side effects. Then you say, okay, passed. But often what happens is it goes up to monkey, but on humans, lot of side effects, lot of problems. So then, I'm going to stop here because let's not do this. Let's just discuss what we are trying to solve here. Okay, so yeah, so there are, all these things where drug design today is really about taking things in a test tube, and that's why it takes 5 years. You have to, at every stage, take it to mouse, give it to mouse, then take it to monkey, give it to monkey. If monkey is alive, then you take it to human. And that process takes a lot of time. So people are trying to see which parts of this process that you are doing in the test tube can be taken to the computer for simulation. And that's where the quantum computer comes in, because the quantum computer can solve some of these problems. It can simulate. Remember, I talked about the caffeine molecule. Okay. So these are the things, and that is why okay, the 10-minute free time, just type IBM Quantum on Google. It will take you to a website. On that website, create an account, just like you created a Google account. On that account, once you have created that account, it will give you 10 free minutes. Okay, but you need a credit card for this. The primary reason for needing a credit card is certain countries are not allowed to access this. So they want to make sure that you are an Indian who is accessing this system. Okay. So the 10 free minutes, please, you just type IBM Quantum and start using it. Okay. Yes, there are funded pilot projects, lots of them. National Quantum Mission is one. The Department of Biotechnology was another. Then there are funded projects that you can go to for ANRF and various places. Funding today is not the problem. Ideas are the problem, So you need to come up with a good idea. Once you have a good idea, you will be able to raise the funding, because government of India, government of Andhra Pradesh, all governments are very, very keen to help people who can solve real problems. Please give some examples. Deep learning application. Yeah, so pick any deep learning application. Whatever you are running on classical, try and run it on quantum. That's it. Very simple. It can be the cat problem. Cat problem is you are looking at identifying cats, a machine learning problem. Let us say you have built a classifier to classify cats and dogs. Okay. You are given two sets of images, cats and dogs, you mix them up and you have to classify whether it is cat or dog. Now, the same machine learning problem, please try to solve it on a quantum computer. Okay, so it might not yet be deep learning, but it will be quantum machine learning. Okay, so you can do that. Single photon circuits used in quantum computing. Can we say single photon can carry a lot of information? See, single photons are also qubits. Okay. So you all might have learned that qubits, if you have qubits, you can carry information in them. You can do processing with them. Okay. So all these things you can do, right? You can solve problems on your, using quantum machine learning or using these photons and all. But so far, photonic quantum computers have not been very successful, but photons have been successful in the kind of work that you just heard in the previous talk from Dr. Anil Prabhakar, where they are doing communications. So a lot of communications does happen using laser lights and all of those. And for example, Dr. Anil Prabhakar is trying to use encryption of these signals. So yes, I mean, photons do carry information just the way any other qubits also can carry information and you can use it in computation. But of course, single qubits will not be sufficient. You need multiple of them. And that's why I've been telling you that, the number of qubits has been increasing. 2016, 5 qubits, 2025, 156 qubits, and this number keeps going up year on year. Okay. Yeah. So I think we are well over time now. So I will stop here, sir. And thank you so much.
Yeah, for the other questions on programming and other things.
Sir, just a moment.
Yes.
Sir,
Yes,
our
sir,
chairman sir want to join. Just stay back,
Yeah.
sir.
Sure, sure.
Meanwhile, I connect him, sir.
Right.
Thank you,
Yeah.
sir.
Thank you so much, Venkat sir, for joining and sparing your valuable time. Dear participants, some more queries that you have on programming and Qiskit and other things, you can refer to the course QT-03, which is already conducted. I have shared some of the ways that you can look up. Just go to YouTube, type QT-03, and then type MNIT and EICT. These three keywords, you will go to that playlist. You can watch all the videos. There are some sessions on quantum machine learning as well. So please go and watch those videos. On Qiskit, there's a very clear video on how to set up and do that. We will conduct those courses. Please just hold on. Don't rush. Don't hurry.
Yeah.
Right? There is a lot
Yes,
of
sir.
time.
Actually, the enthusiasm is great. People want to do
Yeah,
everything today itself. But sir
Correct.
has already, I told you, he has already conducted 4 of these courses in the past. Okay. To thousands of students across India. And this is the second time they are doing it. A lot of that first time course material is already there for everyone. But sir is going to make sure you are also going to, get this, you are also going to have it very soon. Okay. So it is very important. All of you just stay tuned, stay on it. These questions are all great questions, very good, which means you are all engaged. But sir has a plan. This one was QT1. Now QT-02 will happen, then QT-04 will happen, 5. So one by one, you are going to, become experts very quickly.
Yeah, so we will continue to listen to Venkat sir also. So you can understand being a country level leader for a very big organization like IBM, sparing time. Especially, he has a very strong inclination for motivating faculty because you will in turn motivate the students. So that's where his heart is, and he is found in many such events where faculty and students are benefited. And then he's been a kind of mentor for all of us. So we thank you so much, sir, for your session and for your
Sir,
time.
you.
Participants, please don't worry and let's go slow because quantum will take time to digest. It is not a fast food item. Please understand that. So please be patient and go slow. Aram se. There is no nothing to rush, and we can very much take it forward, right? So 1 minute, our chairman sir is joining. So let's see. Yeah, Srikanth has joined. Sir
Good
is
evening
joined.
to you all.
Good evening, sir. Good evening, sir.
I understand we have come to the fag end of the first module
Yes,
that we
sir.
have launched. Then it's so nice to see Dr. Venkat Subramaniam here at this point. Also, we are very thankful for you to lead us and handhold the entire program with Dr. Emmanuel Subhakar, who has taken up the entire burden and meeting our own expectations. It's so nice that about a large number of our faculty members have shown keen interest in taking up this challenge of preparing themselves for the quantum technologies. And the response for various proposals, project proposals, as of establishing the UG laboratories, teaching laboratories, and also the algorithms was extremely, high, the response that we've got. There are several, in fact, almost proposals to the extent of 2,500 crores have been proposed on both the sides. That's what I understand. You can see the enthusiasm amongst people. Sir, I think with your support, with Dr. Emmanuel Subhakar taking all the load, and with the support of Dr. Anil Prabhakar, and of course, JBV Reddy, Dr. Sridhar, we had the gamut of people who were stars in this particular activity today. We want to see that this initiative of faculty development and capacity building would go a long way. And we have how many more? 10 more modules to complete.
Yes, sir. Yes, sir. We have combined 00 and 01. Similarly,
Yeah,
we'll
00
combine
and
03
01.
and 04. So we'll be 10 modules in all.
There are 10 more modules, yes. And I hope the faculty initially, the response was that there was a little difficulty in coping up with the sort of initial mathematics that has been put in, but hope they would be able to appreciate why this has been a part of this foundational program as they go through coverage of the other modules. And I think one of the suggestions that has come through is to make it more succinct, in the sense to reduce the mathematical component in a physical manner to understand. And I hope the implications would only mean that they need to work at home rather than listening to the lecturers on the mathematical part of it. So that seems to be one of the responses. But as I see, many of them have participated in the assignments, and almost all of them seem to have been showing. How many assignments were over? I came to know only about the 2 assignments.
So 2 are over, sir. We are doing the third one tomorrow. So after today evening, we'll start the third. We'll complete, we'll keep it open till Saturday. And mostly by Monday, we'll try to issue the certificates for those who complete.
Great. And when is the exam test being run for the Oh, for the first module, we have no.
No, sir. After a few modules, we'll have a face-to-face meeting. I think that we'll have to discuss with IIT Madras and CDAC, that
Yes.
meeting, and then we'll have a written test at that time.
Yes.
That will be.
Sir,
there. They'll have time to
initially-
prepare also, because this is QT-02. Once we complete, they'll be comfortable with the physics and maths part of it, sir. Yeah.
And
that's-
very relevant to this, I think today morning, we also had a program at VIT-AP on National Semiconductor Technology Symposium, where quite a few researchers, there were 3 MOUs signed, and people from Siemens and several other industry partners have also participated with CIA, AP, ITAP, and so on. There was a good response for the program as well, and we were referring to our activity that was going on at that particular moment. Well, I hope sir, have you taken the feedback from the participants?
We are yet to take it, sir. We'll send it shortly. Now we'll have the valedictory session. In that we'll listen from some of the participants. They are also waiting. So once we
yes.
conclude our session now, we'll have the valedictory to conclude from 4:30. Yeah, another 15 minutes. We'll listen to the participant. If you are there, it will be good, sir. You can listen to them.
I would be there, sir.
Yeah,
I would be there.
Venkat, sir,
Please go ahead.
would you like to carry on, or you have some other engagement? Please.
Yeah, I will carry on.
Yeah.
But
10,
I
15
want
minutes
to
will be.
thank both of you, Pili sir and Dr. Madhumurthy also, because you are doing this at a big scale. That scale is very important. You've brought together almost every important faculty together. And at the same time, Madhumurthy sir, I must say that you are doing that hackathon also, beautiful parallel
Sir,
activity for students. Yes, sir.
with your support, I think we were able to enthuse many students from various campuses. I believe there are close to about 3,000 teams participating in this,
Correct,
and that's wonderful.
Amazing.
Awareness, really amazing,
Yes.
really amazing.
Yes, and
In
you were
one go.
talking, yes, sir, and you were talking about, making this course practical. The only
Yes.
way to make it practical is by connecting the faculty who have now learned the theory and those students who are now capable of solving some problems. You bring them together, and that makes it practical. The professor now comes up with a problem saying, okay, look, this is something I would like to solve in physics, chemistry, biology, engineering, whatever. And that student who has now learned how to run Qiskit programs and things. So this
Yes.
is a beautiful next step, is for you to just make them come together. That's it. And you have solved a beautiful problem all by yourself. You've
Sir,
created all the right ingredients, sir.
I think the support that you all extended made it possible. We were only facilitating this process, but you were the real, bringing in judges from the industry.
Sir,
participation.
I must say that, it is much more than that, because the same advice we have been giving to many people. Okay. But what Pilli sir